Recording.
So we are talking about transverse mechanical waves. And we're looking at the general equation of a one-dimensional transverse harmonic or sinusoidal wave. So we saw the wave equation is given by this kind of a term. Now remember, frequency is a property of the source. Source is, in this case, a simple harmonic oscillator. We saw that K is given by omega by V, where V is the propagation speed. Now the propagation speed this is dependent on the medium's physical properties. Tension and linear mass density. Phi is a phase constant, and E is the amplitude. Okay, so these are the general terms in the standard equation of a harmonic one-dimensional transverse wave. So we had seen that there are two ways of interpreting this equation. If we freeze the value of t, then we have a snapshot. If we freeze the value of x, we have the oscillation of a particular point. On the medium. Okay. So this is what we had understood in the last lecture so far. Okay. Now today we will begin by understanding a couple of more terms. And the first of them is the concept of wavelength, which will be understood from the snapshot picture. Yeah, Sujat, we'll discuss about that some. That was there in the last lecture. Okay. I'll just take you through that sum. Okay, so you're discussing about this particular wave and the snapshot picture at various times. So this was the question we were discussing. Okay, so given this equation, we wanted to draw the snapshot picture at these various different times. And then we wanted to write the equation of oscillation for the medium particles at those particular points. So we had discussed about the snapshot picture at t equal to 0, t equal to 5 milliseconds. So let's do a run through of this particular question again. So obviously by looking at this equation, comparing this equation to the standard equation, okay, we saw that so these are all these properties. Now let's concentrate on this, the snapshot picture at various different times. Let's look at this concept again. Okay.
Okay.
So y at t equal to 0, the snapshot picture at t equal to 0 was 12 sine minus pi by 6 x plus pi by 6. Then y at t equal to 5 milliseconds became how much? It became, so this term 50 pi t at 5 milliseconds comes pi by 4. Then at t equal to 10 milliseconds. So we'll plot each of these, okay, but before that, let's just understand the terms. And finally, at t equal to 20 milliseconds, so these were the 4 snapshot pictures. We have to plot them, of course, but they are the values at this various times, okay. So next we will plot these 4 snapshot pictures, okay, at these various different times, 0, 5 milliseconds, 10 milliseconds, etc. This last one is 20 milliseconds. I can also see one thing over here, that the time period of oscillation for this particular wave, frequency was 25 hertz. Okay, so that is 40 milliseconds. So we are seeing that this 5 millisecond term is actually 1/8 of the time period. This 10 millisecond term is 1/4 of the time period. And this 20 milliseconds is half the time period. Okay, so now let's start plotting each of these. So this term can be understood as because sine is an odd term. Okay. So sine of minus theta is minus sine theta. So to plot this, you can start by understanding what is the graph of minus sine theta like. It's like this. Okay. So now how will the graph of this one look like? So this point becomes the origin now, where pi by 6 was, that becomes the origin for this one.
Graphs show F1.
So correspondingly, this graph will be a term like this. Oh, wait. This is not correct. The graph will shift towards the right, not towards the left. This point will shift to the origin. Minus pi by 6 point will shift to the origin. The whole graph will shift. This graph will be like this. So at theta equal to 0, see the value will become plus half. And theta equal to pi by 6, this point will shift here. Okay. So correspondingly, we see this graph. This kind of a situation. This is the snapshot picture at t equal to 0. So this point here will correspond to x equal to 1 centimeter. This point here will correspond to 7 centimeters. Like this. Now, if we compare this snapshot picture to the next one, I'm going to draw at t equal to 1/8 of the time period, which was 5 milliseconds. So we saw so we can of course write that like this. So pi by 4 plus pi by 6. So we will see that we look at so if you compare this graph with this graph, subtracting minus pi by 4. So the point here which was at minus pi by 4, that shifts to the origin. Okay. This point will become 1 by root 2 now. And this point will become pi by 4 plus pi by 6. So that is 5 pi by 12. So if we plot that again in this diagram, you can see that this snapshot picture like this. So you'll see that the wave has shifted by an amount of 1.5 centimeters in a time of 5 milliseconds. So that's how we can understand that this justifies the fact that the wave speed okay. Now the next snapshot picture that we'll plot will be easier because it is at t by 4 and t by 4 corresponds to a phase change of pi by 2. So this term here, instead of pi by 4, it will become pi by 2. So that can be written as and cos being an even function. Like this, okay.
Yes, sir.
So we will plot this snapshot picture, this one, and we'll compare it with the one at t equal to 0. Okay. So do one thing next. Plot the snapshot picture of this 10 millisecond in a diagram and superimpose it with the one at t equal to 0. You need not make the one at t equal to 5 milliseconds because 3 of them in the same graph will become a little confusing. Okay, so let's superimpose the two graphs and we'll understand. X was in centimeters. So our t equal to 0 graph was looking like this. So this was at t equal to 0. So this point here was 1, this point here was 7, this point here was 11, sorry, 13. So 6 millimeters minus 12 plus 12. Now when we superimpose y at t equal to 10 milliseconds, I think it's becoming there's this term. Okay. This graph shifts in such a way that interestingly like this. Sorry, disturbance.
Let me start from one.
Yeah, it shifts like this. So this is quarter of the time period. See that this shifts by 3 centimeters. So again, your V like this. Okay. Now on this, if you superimpose the earlier graph that we had drawn, you'll see that it was you can understand how the whole wave shape is traveling or propagating. But at the same time, the medium particles are not propagating. So medium particles are only oscillating. It is the shape which is propagating, the shape of the string. So for example, you can see the particle which is located at x equal to, for example, 4 centimeters. At t equal to 0, it was at the negative extreme of oscillation. Okay. But by the time you come to t equal to 10 milliseconds, it's come to the origin. So it's oscillating up and down like this.
Yes.
Similarly, if you now see at t equal to 20 milliseconds, which is in fact half the time period, you will see that your y becomes like so. This is not only drawing the snapshots, but superposing the snapshots on the same diagram. So you can understand how the shape of the string is changing from the red colored wave at t equal to 0 to the green colored at 5 milliseconds, then to the blue colored one at 10 milliseconds, okay, to the violet colored one. So the whole wave shape. So comparing the snapshots, okay, we can see that the shape, which is a sine wave, travels along the x-axis. So that is the axis of propagation. at a speed v is equal to omega by k here, which is 3 meters per second. But at the same time, the medium particles, you can understand, they are not traveling, they are only oscillating. In this case, in SHM, along the y-axis, which is the transverse axis. With frequency equal to omega by 2 pi, or in this case 25 hertz, amplitude equal to 12 millimeters. So this is the interpretation also that we see from the snapshot pictures compared at various different times. Okay, so drawing these shapes becomes a little technical in terms of interpreting the graphs and drawing the exact sine curves and all, but hope you've understood the general idea from this. Now we come to the other part of the question, which is about, okay, so we have seen the snapshots at various different times. Okay. Now we want to write the equations of oscillations for the particle at x equal to 0, 3 centimeters, etc. So let's look at this part of the question next. Okay, Jagannath, I'll wait. Okay, give you some more time to write down that part. Okay, so this diagram above has the all the three or rather all the four different snapshots at 0, 5 milliseconds and 10 milliseconds and again 20 milliseconds.
Done, sir.
Okay, so now let's look at the second part of the question, where we are looking at the particle oscillation equations at various different times. Oops, not this entire thing. Actually, we can once again complete it. So you can complete it here only. So we can see that at x equal to 0, if you just substitute x equal to 0, so the equation of oscillation of that particular medium particle, which is located at x equal to 0, as a function of time, you will see will become 12 sine 50 pi t plus pi by 6. You can see it's an SHM with amplitude equal to 12 millimeter, frequency equal to 25 hertz. Okay, and the initial phase constant as pi by 6. But similarly, if you plot at x equal to 3 centimeters, you see it is 12 sine 50 pi t, okay, minus pi by 2 plus pi by 6, or 12 sine omega t minus pi by 2 plus pi by 6 will become minus pi by 3. So in comparison, this one now is an SHM with same amplitude, same frequency, but with a phase term of minus pi by 3. If you compare these two, they are SHMs with same amplitude equal to 12 millimeters, frequency equal to 25 hertz, but phase difference of pi by 2. Similarly, if you see this one, now for example, this and this, they have a phase difference of pi. Okay, so through this, what we can understand that all the medium particles are performing SHM with common amplitude and phase constant. Common amplitude and frequency, but they have different phases of the SHM. And the phase difference between any two particles actually depends on the distance between them. Okay. So we'll look at that interpretation next. So coming back to the general equation, what we can see is that from the snapshots, okay, at various values of time t, we can see that the shape of the medium, which in this case is a string, is a sine wave which travels along the x-axis at v equal to omega by t. Whereas from the oscillation equation of various values of x, you can see whereas here when we take a snapshot picture at some particular instant t naught, we can see it becomes a function of x. So that function is interpreted this way. We can see that this is all particles are in SHM along y-axis at common amplitude and frequency. Now the most important thing, the phase difference in the SHM of two particles, let's say at x equal to x1 and x equal to x2, depends on the distance between them. Okay, let's understand this term next. So just make a note of this point. So the two interpretations, the snapshot picture interpretation and the value of y as a function of time for a particular x. Okay, so now we bring in the concept of wavelength. Or lambda is a symbol used for wavelength. So for example, we were looking at snapshot picture at various different times. Okay, and we saw that it's basically a sine curve which is traveling, sinusoidal shape which is traveling. So let's just for reference, suppose so see that as this is traveling, this is at some t1, this is at some t2 equal to t1 plus some amount of time, and this is at some t3 like this. So we can see that the distance between two crests always remains constant as the wave shape travels. So that's one way to define the wavelength. This distance is always remaining constant. Okay. Or that's the same as the distance between two consecutive troughs. The nature of the sine wave, okay, the symmetry of the sine curve, that crest to crest will be the same distance as trough to trough on the graph, on the shape of the curve. It's like that. So that's one way to define wavelength. That is the distance along x-axis between two consecutive crests or troughs, like this. Okay. But there's also another way to understand it, which is on the basis of the particles. Okay, so if you look at any two particular particles, like this particle located over here, which is x1, let's say, this particle, let's say, located here, x2, this particle located here, x3 and x4, etc. You can see that if we have the general equation of wave like this, then the equation of SHM of one particular particle is like this, and the equation of SHM of another particle, any particle, need not be this x2, which I've shown in the diagram, but we compare the equation of SHM of any two particles, it's like this. So the phase difference between the SHM of any two particles, they have phase difference delta phi equal to the difference of these two quantities. So that is equal to k into x2 minus x1. So this phase difference is k delta x. Okay. Now, if delta phi is, for example, 2n pi, that means the particles x equal to x1 and x equal to x2 oscillate in phase. Okay. If delta phi is, for example, 2n plus 1 pi, they oscillate in opposite phase. So they'll be oscillating like this. By the time this reaches here, it should be here. This kind of oscillation they'll be having. So here we can see that if delta x is equal to lambda, that means x1 and x2 are the nearest two particles which oscillate in phase.
Sir, can you explain this point again?
See, it's all according to the equations. Just follow the equations from here onwards, from this step onwards. So the equation of SHM of two particles x1 and x2 is given. From that, you're understanding the phase difference between them. So if that phase difference happens to be 2 and pi, that means they are in phase, na? Because sine of 2 and pi is 0.
0.
So if delta x is equal to lambda, then they are the nearest two particles. Okay, so that means delta phi is equal to 2 pi implies that delta x is equal to lambda. So k lambda should be equal to 2 pi. So if the distance, if x2 is equal to x1 plus lambda, okay, then so now because this is 2 pi, you can see that these will be the nearest two particles in phase, because the difference between them is equal to one wavelength.
Sir, basically distance is basically less than lambda.
Then the phase difference is less than 2 pi, so they cannot be in phase.
Okay. In a single phase, they want to do, then it should be minimum lambda.
The minimum distance between any two particles, if they are in phase, if the oscillation is in phase, is lambda.
Okay, understood.
So that's the way to define the wavelength in terms of that quantity, that how we'll relate it with particles which are in phase.
So that is delta x equal to lambda.
Yes. If
What
phase difference delta phi is 2 pi, then that means delta x is equal to lambda.
sir, after that is kx or k lambda?
K lambda beta. Delta phi is k delta x. No?
Yes, sir.
So if we substitute delta x as lambda, then that delta phi becomes 2 pi. So from that we are getting the relation that lambda is equal to 2 pi by k. Sorry, this equation should be 2 pi by k. So this thing now we are substituting in this general relation. So in this general relation, if this happens to be lambda, then this should be 2 pi. Understood, no?
Yes, sir. Yes, sir.
Okay, so now we see that there is this important relationship between the constant k and wavelength. Okay, so when we had seen the general equation of the wave earlier, we had seen that in this equation we had related k only in terms of wave speed, propagation speed. Okay, so we'd seen that omega was 2 pi f, where remember f was the property of the source, was the source frequency. And then we had seen that k was omega by v, where v equal to omega by k was the propagation speed, which depends on medium's properties. But now we also see that k has another very important significance, that it determines the wavelength. You can almost think of the wavelength like the size of the wave, size of the sine curve along the x-axis, that kind of thing. So this lambda is again related to like this, v is equal to f lambda. Okay, because omega is 2 pi f and k is 2 pi by lambda. So you're getting this. Okay, so in this relation you can see that v depends on the medium's properties. Okay, f depends on the source. It is the source's property, in fact. Okay, whatever is the frequency of oscillation of the source, that will dictate the frequency of the wave. Okay, so lambda depends on both the source and the medium. So that's one thing. Okay, the other thing is that for any two particles at x equal to x1 and x equal to x2, the phase difference of their oscillation that is k into x2 minus x1. So it is 2 pi by lambda into delta x. So just make a note up to this point, then we'll discuss more about this. So there is an important relationship between delta x and lambda, which tells us about the phase difference between two particles.
Sir, can you scroll up for a minute?
Yeah.
Yes, sir. Done.
So now coming back to this point here, you'll see that if delta x is equal to lambda, then obviously the phase difference is equal to 2 pi. But for example, if delta x is lambda by 2, then the phase difference is pi. So they will be in opposite phase. Okay. These will be in same phase. And in general, if delta x is equal to 2n pi, sorry, if delta x is equal to n lambda, then your phase difference will be equal to 2n pi. Here n can be any number, need not be a whole number also. Okay. So for example, if the wavelength is 6 centimeters and delta x is equal to 1 centimeter, then your phase difference is how much? So you can see that in this case, delta x is equal to 1/6 of wavelength. So phase difference will become 1/6 of 2 pi. So it will be pi by 3. Okay. So we'll understand all these things with an equation. I mean, with an example. Okay. Now, before we come to that example, one more very important thing. Propagation speed we had seen earlier. Now, this depends on the medium's physical properties. So in this particular case that we are discussing, transverse waves on a string, the medium is the string. Okay, and the properties that determine it are tension T and linear mass density, that is mass per unit length, mu. So the relationship here is this. We will do a proof of this later also. So V in meters per second will be square root of tension in newtons divided by linear mass density in kilograms per meter. So this is another important relation. Okay. What? Now, Baba, come here. Okay. Okay, so let's understand this with a final example, which will crystallize all these concepts for us. Okay. So in this example, imagine we are actually carrying out an experiment related to waves on a string. So this x tends to infinity on this side. So this is a thread at tension T equal to, let us say, 400 newtons. And it has a linear mass density of, let us say, too much. Let's just say the linear mass density is it's a very light string, as you can see. Okay. Now at x equal to 0, the point x equal to 0 is attached to an oscillator that vibrates it along the y-axis with an amplitude of 2 millimeter, frequency of 10 hertz. Okay. So first of all, determine wave speed, omega, k, and lambda for the resulting wave on the string. Write the equation of the wave if y at x equal to 0 is 0 at t equal to 0. We want to find the phase difference between two particles A and B at XA and XB. So just start with the first two parts. I'll tell you what to do in this third part. Just one small correction here. We'll make this 1.6 gram per centimeter instead of 16 or 0.16. Just make this 1.6 gram per centimeter. Okay, just try out this question, people. Step by step, try to relate each of the quantities with the concepts that we have discussed. Okay. For example, frequency of the wave is the property of the source, whereas wavelength is a property influenced by both the medium and the source. Propagation speed depends on the medium properties. Okay, let's check the answer. So from this information here, you can see that the wave speed, but only thing is you have to convert this to proper units. So this will become 1.6 into 10 raised power minus 1 when you convert to kg per meter. Okay. So this will become so 50 meters per second should be the wave speed. Now this will determine the omega. So 20 pi radians per second. Okay. And then you have P is equal to omega by K or F lambda. So you can see that the wavelength will become 5 meters, and accordingly K will become 2 pi by 5 radians per meter. So these are all the quantities: wave speed, wavelength, K, and omega. So this becomes the starting point for problem here. Okay. So the general equation is like this, let's say, where we now know that amplitude is 2 millimeters, omega is 20 pi radians per second. Okay. So now we can see that the equation of SHM for the particle at x equal to 0 is E sine omega t plus phi. Now this one, this is 0 given, and it moves to the positive side. Therefore, the phase constant should be 0. So the equation of the wave becomes 2 sine 20 pi t minus 2 pi by 5 x, where y is in millimeters, t is in seconds, and x is in meters. Okay. So now, having understood this, just apply the relationship between path difference or x2 minus x1 and phase difference delta phi for the last part. It's quite easy. This when you solve the third part, so you can see so phase difference. Understand this directly like this also. This is one way to understand it, or another way to understand it is that you can write out the equations like this and understand it. Okay. Okay, so with that we complete today's session. I will send you the recording and notes of this session soon. So you can start with HC Verma questions. Transverse waves on a string, that chapter. It's in part 1. You can do from question 1 to question 22. That's it for today's class. Thank you people for attending. Wish you a happy Ganesh Chaturthi and see you next week.
Thank you, sir. Bye.
Thank you, sir. Bye, sir.